this formula. So this is the phi 0 lifetime, and this is the width, phi 0 going to gamma, and I had asked you to work this out. Can somebody tell me now? Plug in the numbers and tell me what is the answer you get. In C squared, I missed the square the other day, 576, 5 cubed is correct, and that's phi naught square. And I've given you a reference to a rather recent paper, which gives a precise measurement of the phi. So here, 0 is 92.7, and you all know that M50 is 1.5 MeV. Can somebody work this out and tell me what the answer is? This time there are no mistakes. Yeah. I think so. Let's start. Good. Please focus in your calculators and tell me what answer you get. There's no hurry. We're going to do exercise like this in class continuously as we go along with it. The reason for looking at this example again is it's one more direct piece of evidence is the number of colors. But of course, it doesn't tell you that the underlying gauge group is SU3, but it just says that the number of colors is 3. And later we'll have to figure out why it is, and the most conclusive proof that it is actually SU3 comes from the renormalization group running of the coupling constant of SU3. 7 what? What? Very good. So now how about computing the lifetime of phi 0 going to gamma is 1.1 by 7.68 EV downstairs, where we have to multiply it by something. Okay. What's the something? No. Lifetime. Lifetime should be in seconds. No. So this is in natural units where h bar equals c equals 1. So if you have to convert it into times h bar. What's the value of h bar? Somebody look it up and tell me. I know the number, but I want you to look it up somewhere, anywhere, particle data group, so that it stays in your mind in reasonable units. So it's called the Planck's constant of action, and action is energy times time. Okay. So h bar, somebody find me in some reasonable units. So obviously we want to get rid of the EV, right? So we want to express it in terms of an energy like an EV or an EV times a second. So you can Google physical constants in particle data book and look it up. Hmm? 6.58 times 10 to the minus 16 EV second. So let's put it in and let's get the number. 0.58 times 10 to the minus 16 divided by 7.68. So this is in seconds. So what is it roughly? It will be something like 8 times 10 to the minus 17. 8.56 times. Do you like this number? Is it a good number? Is it a big number? Is it a small number? Good number? Bad number? You should have some opinion about this number. So what do you think this is? What kind of a number is this? And what kind of number would you like to compare it with? After all, you have to calibrate the scale somehow, no? So some of the lifetimes that you're aware of some unstable particles is what you should compare this with. So what is the typical scale of particle lifetimes that you know and that you're aware of, or that you should be aware of, even if you're not aware of? Good. So you can look up a couple of lifetimes of some your favorite particle and give me some numbers so that we know what's and for all. For instance, let's look at the lifetime of the muon, lifetime of the 5 plus, for instance, lifetime of the neutron. Anything else? For the moment, anyway, this is enough. Please look up and let me know what his lifetime is.
Muon that times 2.2 minus 6 seconds.
Very good. 2.2 times into minus 6 seconds. So microsecond. So that's the reason why one of the LHC experiments is called compact muon solenoid. Muon solenoid, right? Because of all these particles, the muon is the longest lived. So on this particular scale, if you say that by 0 10 to the minus 17, this guy's lifetime is 11 orders of magnitude larger. Okay? So it is practically infinitely long lived. And that's the reason why the muon is such an important particle in particle physics. Because you can do a lot of things with the muon that you cannot do with other things. The other day you asked me about the G minus 2 the muon. It's because its lifetime is long that you can do various things. Okay? And its mass is also reasonable, so you can look at effects because its mass is reasonable and its lifetime. What about this?
Around 26 nanoseconds.
26. 26 nanoseconds. Okay, fine. Then this.
This is neutron, right?
Yeah.
15.
So how much is that in seconds? Roughly. Roughly. The order of. Now these two are both caused by the weak decay, right? This is a weak decay and this is also. How come there's such a huge difference I mean, literally, this is 12 orders of magnitude. How come? With the same interaction that it was possible for these decays, then we should ask why is it the lifetimes are so. Hmm? Somebody has to tell me, no? Otherwise, what's the mass? Hmm? Maybe because mass difference. Neutron is very heavy, so it ought to decay even faster. No. The reason is the muon has a certain mass and is essentially decaying into particles that are massless. On the scale of the muon, the electron is 200 times lighter than the neutrinos have. Okay? So it's like a massless particle is decaying into massless. Whereas the neutron is decaying into a particle that's almost the same mass, almost the same, right? The mass difference we saw the other day, if you remove the electron mass also, it's only 782 keV, which is a very small number. Okay? So the allowed phase space for this thing to decay is so small that it is good. Okay? Now the neutron is indeed heavier than the proton, it can decay. But then how is it that the neutron doesn't decay? Neutron has a proton and a neutron. So how come the neutron doesn't decay inside? How do we know neutron doesn't decay? Well, it's present, no? There's heavy water present in the oceans, which are probably as old as the Big Bang itself. All the deuterium was probably produced in the Big Bang and it's still around. It means that it's infinitely long lived. So how come the neutron in the neutron doesn't decay? Hmm? Any idea? Right. And so the binding energy of the deuteron, how much is the binding energy of the deuteron? It's 2.2 MeV, which means that the effective mass of the neutron becomes less than that of the proton inside the deuteron, and so it cannot decay. It's not possible. Okay. So these energetics are extremely important in determining the lifetimes. And most of the time, all these integrals are very difficult to, very complicated to calculate. And sometimes you just go to the computer and you just evaluate such integrals. numerically. So I want to actually go through this book of Griffiths. Essentially, I want to go through sort of
Can you repeat the argument about neutron not decaying inside of
the binding energy per nucleon for deuteron is 1.1 MeV. Right? So it means that the neutron is trapped inside, and you actually need excess energy to actually break up the deuteron. So so as he said, it's only the free neutron which can decay because it is heavier. Now there's something called the mass defect, which makes the mass defect for any nucleus is equal to the energy that is needed for it to actually form. So it is formed in such a way that the individual constituents can no longer decay. But that's not true for the triton. What's a triton? Two neutrons. So there it is unstable nucleus. So even though it forms, it will decay because the binding energy is not enough. So it forms, it has a width, and so on. You can't keep on producing nuclei that you like. For instance, even if it's carbon, you can add at most 8 neutrons to 6 protons. You can't keep adding more and more because it just doesn't form. So the energetics are necessary for you to figure out how a neutron can form from constituents. So was the discussion here about pulling out the Feynman rules and this Gaussian integration? So it's actually such a beautiful formula that you should have a look and stare at it a bit more and see exactly how the variance comes as a second moment of Gaussian distribution and why it is that the two-point function is such an important. At least I'm impressed by the beauty of it. Of course, beauty and all is a matter of taste, and not everybody may agree on what is beautiful and what's not. Any questions about that particular discussion? Because I know that most of you have had it in class already. I thought that it's important for me to remind you, because when you talk about the standard model, it means you're talking about interactions that are described by Lagrangians, and the Lagrangians are determined by the various particles in the species that define the Lagrangian and the standard model associated with each of the species. You have propagator, and then we also saw from that particular expression for the generating function of the Green's functions that that you read the Lagrangian, you read from the Lagrangian what the vertices are, because you write Li of delta by delta phi. That means that the final rules are generated by the interaction part of the Lagrangian. You just have to pull out that term, and that is going to determine the vertex. Okay, so there will be. So any other questions about the long discussion we had? There are also many useful comments from students about conserved quantities and all these things. Anything else? No. So I tried to go through these chapters and so that you can read these very effectively and very simply. So let me see what this chapter 2 of Griffiths is. So this just introduces you to electrodynamics and very quickly tells you how to draw the Feynman rules, the vertex. This is the vertex. So the vertex basically is read off from the Lagrangian. And you have only one power of the electric charge, only one power of the electric charge of E, right? But if you have two powers of the electric charge, for instance, you can produce a scattering, a simple three-level scattering. Three levels. Why tree? Tree in contrast to what? If it is not a tree, then loops. So here is a tree, and this is the bone approximation. It's also the classical approximation. If you have one loop, what kind of an approximation is it? If you have one loop, one loop. No, if this is a classical approximation, is tree is classical, then what is one loop? It's semi-classical. So this means that there are terms of order h bar are included. So there are two kinds of expansions that you will come across in field theory. One is expansion in powers of the coupling constant, powers of, say, lambda is a generic coupling constant, or expansion in powers of h bar. Powers of h bar. And you must have seen this, that in field theory, this is generating functional of Green's functions, functional of Green's function. And this thing here leads to generating functional of proper vertices. And these are related to one another through a Legendre transformation. So such things are of importance when it comes to renormalization theory. So these things are important for renormalization theory. We don't bother about that in this course because we already know that the standard model is renormalizable, and then we leave it to experts to prove that it is actually renormalizable, and we just let happen with this. Okay. So this is a generic scattering. So you can have specific scattering processes like Hava scattering, which has two diagrams. One so-called annihilation, and then there is a scattering diagram. So together you have this. In contrast to say E plus E minus, so Baba is E plus E minus. On the other hand, if you have E plus E minus, E plus E minus, it's just only one diagram like this. Okay? So this is the simplest possible diagram. And it is used as calibration, used for calibration. So this is with two vertices. But these are not the only diagrams, but you can have other diagrams with just two vertices. For instance, you can have pair annihilation.
So why can't Baba scattering be used for calculation?
If you look at the Baba, and then you will see, just like with Rutherford scattering, you can't have the total cross section because it's divergent. There's this 1 by 6 to the power of 4 theta by 2. So that means that you can only do it for, you must have a cutoff for the angle. So that's the reason. And this is very pure, very simple. That's all. Can someone guess for root S much larger than mu? What is the cross section that you will have for this? I want you to guess from the old formula that we had for Thomson. Thomson scattering. So sigma t, let me call it. I think you people have educated me as to what this might be. 8 pi by 3, right? Alpha squared any. And you people have plugged in various numbers and you have calculated what this is. Let's do this one more time. Calculate this so that it's fixed in everybody's minds. So here we will need h bar c to be 197 MeV femtometer, right? So please calculate this again and tell me what this is. 8 pi by 3 times 7 squared times MEC squared, sorry, otherwise dimensionally we have a problem, times 197 squared. So that will give me in femtometer squared, right? And how do we convert that into barns? So 1 barn is 10 to the minus 28 meters squared. Right? So this is equal to 100 femtometer squared. Now, I'm just giving these numbers, I'm not sure, please check. Let me know what this is. Somebody had done this in the class. Doesn't matter. Running these numbers again so that it's cemented in your minds once and for all. So when you reach my age, somebody wakes you up in the middle of the night, right? I like this guy. He does even this in the laptop. See your point? Sure. Check this. Google it and tell me what the constant cost is.
So,
Yeah.
what is the cases per term sigma over H bar?
So this here,
What is it from?
H bar C.
For that, yeah.
What does it say? Yes. Yes, it's correct. Okay. Right. So Wikipedia and all of us, we all agree. Now, try to guess for me what this formula is for E plus E minus to B plus mu minus. E plus E minus masses we neglect. We are also going to high energies where we are going to neglect the muon mass. Okay. So just look at that and try to guess what this might be. It's probably not so easy. Okay, so you'll get a factor of E from here, you'll get a factor of E from here. Okay, that's E squared in the amplitude, and therefore in the cross section, you'll get E to the 4 or alpha squared. Okay, so you'll get an alpha squared for sure. Okay, then you will get a 4 pi by 3, not 8 pi by 3, but 4 pi by 3. And in order to get dimensions, so here in the Thomson limit, there's only one mass parameter, which is the mass that you from here, so total masses. So you can only therefore expect only this. Okay. Of course, it may be some complicated function of mass, but it doesn't work that way. It's actually the mass. Okay. Mass squared. So here, what can it be? Hmm? Central mass energy squared. Yes. So good. So you see, Thomson will also teach us the lesson on what kind of answer we can expect for E plus E minus to U plus P minus. And this kind of a behavior is what's called the geometric cross section. Geometric. Of course, the trick is you have to be able to calculate this from the rules of QED, not just I'm waving like this. Okay. So this is for the simplest case. And how about giving a name for this one? E plus E minus going to 2 gamma. What is this? A pair has got destroyed, so this is pair annihilation. You can also have finally Compton scattering like this. And this is where the famous Compton wavelength comes. Now, Roman has a notebook for this. So please download this on FineCalc and try to run this particular notebook. Okay. So FineCalc, please load FineCalc in Mathematica. Mathematica. Okay. FineCalc, and then you can look at Roman. Go to his website, download his notebooks, and try to run it. Has anybody done it so far?
I think I'll fix it fast. It's on their website.
It's there.
Yeah, but
Fine.
electron to me.
Very good. But is it running? So you guys know how to do it. And that's the reason why I set up the Steam page so that you can give a demonstration for the rest of us. Okay? Want to do it?
I haven't looked at it. I have to check the answer. I have to see what it is.
So next Tuesday you'll do it. Okay? See, my job is to set up the Teams page. Your job is to actually give demos, right? So this is literally hands-on learning of these things from this particular notebook. We also mentioned the other day Delbrook scattering, which is already at one loop, so at one loop. So this is light by light scattering. Oops, this is wrong. So Delbrook is light by light. But you can have other scattering of E plus E minus to E plus E minus also. It's higher order diagrams. So these are only higher order. So this is a box over here which will turn out to be convergent, but there are other diagrams which are not convergent. So this has a vertex correction like this. Then you can have something like this, where the photon that's exchanged produces an E plus E minus this. What's the name that we should give this one? Vacuum polarization. And what about the other one, where you can have resting of the external leg like this? So this is the electron says that. So it's not like these things are not observable. These are observable, and this is actually observed already in an atomic system in hydrogen. And this leads to a famous splitting of some degenerate lines. And what is that thing called? Vacuum polarization in hydrogen is called Lamb shift. The Lamb shift is the shift in one of the energies of one of the low lying atomic states. And this vertex here, for instance, leads to G minus 2. To answer your question, it's just dimension for G minus 2. And this was actually measured already in the 1940s, late 1940s, this and this. Of course, there's Nobel Prize for the guys who measured these things. So this measurement was, oops, this was the plan. So these are the simple diagrams of QED, and as we go along, we will use the computer and we'll take help from Mathematica to actually evaluate these diagrams and evaluate these cross sections. Of course, we could also do it by paper and pencil. We've already done it in your class, so your field theory. So if you now went to quantum chromodynamics instead, quantum chromodynamics, which is a theory of what? Quantum chromodynamics. The microscopic Lagrangian N is the theory of what and what? Quarks and gluons, where the gluons also carry color, where the role of alpha electromagnetism is played by alpha strong. So what you need is a vertex, right? And what is the vertex? If you look at the Lagrangian of QCD, you would be able to read off the vertex of interaction of a quark with a gluon, right? It's a basic vertex where you have a colored quark Q with a certain color, say R, goes into. What are the three colors, three primary colors that you people are used to? R, P, G, right? Three primary colors. It's just a name, by the way, nothing to do with what your eye sees, but and then this interacts with gluon, and this gluon had better carry off R bar and B. So this, I don't know exactly what to do. This is going R B bar, R bar B. Thank you. Good. Any other vertices that you're aware of? Should there be any other vertices? Hmm? 3, 2, 1. How come you're so sure? I'm not saying you're wrong, but how come you're so sure? Yes. Okay. But the Lagrangian is not just a covariant derivative, but it's F mu nu, and then you take the trace, and when you pull out the non-interacting part, whatever is left behind. So there's again a trick over there. So if this is G, this is going to have a G, and this is going to have a G squared. That's the important thing. You should keep in mind that this is a G squared. Whereas here, besides G, it will also have the momenta to enter the vertex. Why is it? For the same reason that you mentioned, it's coming from the covariant derivative. So there will be factors of momenta of these gluons also. But the key thing about field theory, coupling constants are not constants, but rather coupling constants are not constant, but what? But are running coupling constants. Running coupling constants. Why is that? So let's again look at QED and see why it should be like that. So for instance here, if you have charge, you have an E plus E minus plus. These are all heuristic arguments. Okay? So this means that this electron doesn't see the full charge of this, but it's screened by the E plus E minus pair. So this is called screening. Screening. And all the running of these coupling constants is governed by what? Governed by denormalization group equations. Gelman law. So these are the various scientists who actually discovered this kind of running of coupling constants in QED. And you can have more screening like this, etc. What about in QCD? Supposing you wanted to draw one loop diagrams, of course you would have a QQ bar pair like this. The QQ bar pair will actually screen, but this is not the only one because there are other diagrams also. The other diagrams like this. And then there's another diagram which looks like this, where you have quartic vertex. So let's give names also, please. So let's give a name. Cubic. What name shall we give this? Hmm? So all these vertices are there. Then later you will see that there are also ghosts which contribute. But ghosts can be eliminated in certain gauges. Ghost. So it's interesting to know, always a bit of history and everything, that the existence of ghosts were actually already foreseen by Feynman, as usual. He said that if you don't have these ghosts, then there's a problem with the unitarity of this theory. He did some simple uh, argument, as usual, heuristic argument, where he figured out that look, if you don't have these ghosts, this was before we had a path integral formulation of gauge theories and before Faddeev and Popov. But still, he was able to figure out just from physical considerations that ghosts have.
What are those?
We come to it. You didn't come, you have not done ghosts. No. Any other interaction I've forgotten about? Now wait. So this is a theory here which has a problem. So it has something called a Landau pole, which says that at large, certain asymptotic energies, coupling constant will go up. Coupling constant. Will go up. Whereas here, so this at such energies it's asymptotically free. But I told you something why it won't always be asymptotically free, right? Because I said that this thing is going to screen, whereas these things are going to anti-screen. Right? So if you had a large number of quark flavors, then the screening because of this may become larger than the anti-screening due to these guys. Here you can't do anything because once the gauge group is known and the interactions are known, you can't keep adding more gauge fields and more ghosts. That part is fixed. Whereas here you can have U quark, B quark, C quark, S quark, D quark, E quark, D prime quark, E prime quark. You can keep on adding quarks in principle, except that nature decides at some point not going to produce any more quarks. But from the point of view of logic and consistency, there is no restriction on the number of quarks. Phenomenologically, we know that it is restricted, or rather, we have not discovered very heavy quarks, but number of quarks has to be smaller than a certain number in order for the theory to be asymptotically free. And then there is a limit which says that 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 there is a quantity which is 2f minus 11n, which determines that f is the number of quark flavors. Number of quark flavors. So a has to be less than something. I think 0. I think it's bounded from that a should not exceed 0 in order for the theory to be asymptotic. So I'm going to leave this as an exercise. Hmm? N is the is the number of colors. Exactly. Thank you.
And this Landau pole is at finite asymptotic energy or infinite?
Finite. It's some very large energy, but finite nevertheless. So where do you think these numbers 11 and 2 and so on come from? So there are many things that we talked about in the gauge, in the group theory part. What are the things that we talked about in the group theory part? We talked about representations, talked about branching ratio, branching rules, all these things. Tensor products, etc. What you do over here is the gauge constant comes over here, G comes over here, and G comes over here. and then you get square of G over here. Similarly, you get G over here and G over here, but there is something more which he just mentioned because of the non-abelian nature, which tells you that it's just not just the coupling constant, but also the representation in which these gauge groups, the gauge bosons lie in. What is the representation which the gauge bosons have to lie in? It's the adjoint representation. Whereas here, these quarks, you don't know for sure. It's probably the fundamental representation. So there will be information about the representation also, which goes into computation of these diagrams, okay? And the representation of this particular thing. So it may not just be a fermion, but you may also have scalar particles. There's nothing to say that in nature we have only box as matter. We also know that there is Higgs, but maybe there are scalars also. In which case, the scalar particle and its antiparticle would also run around in loops. And then there would be a corresponding contribution to the beta function, which also screens. So it depends on the statistics of the particle of the matter, whether it is a fermion or whether it is a boson, spin 0. Maybe there are even spin 2 particles, who knows? As far as we know, in the standard model, it's only spin half particles, spin 0, spin 1. Maybe there are spin 2 particles also. Nothing to prevent their existence as such. Phenomenologically, it's not allowed, but otherwise. So this information will also go into the computation of the beta function as to what is the representation in which these particles are lying in, as well as their statistics. So the corresponding coefficients like 2 and 11 and so on are determined by, so those coefficients like 2 and 11 are determined by statistics as well as the representation as the representation. And if you look in Slansky's tables or any one of these tables and properties in these representations, you will find something known as the quadratic Casimir, quadratic Casimir of the representation, which is a tabulated quantity. So the group representations again come in, and you have to compute the beta function in the non-abelian case. It's always straightforward in abelian theory. Why is it straightforward in abelian theory? Because every representation of U1 is Lagrange. There was nothing to do with it. But even if you go to SU2, SU3, and so on, all the representations can be complicated, and you have to compute properties of the representation. So there's a group theory factor, which is called the quadratic Casimir of the representation, and these things. So very good. So we have now counted for QED, and we have counted for QCD. There's one other interaction that we forgot about. What is that? The weak interaction. Actually, we should call it electroweak, because there is an SU2 cross U1, and this is U1B, which then breaks into U1 electromagnetism. How? Through the Higgs mechanism of spontaneous symmetry breaking, which leads to mass generation for how many bosons? So 3 plus 1, 4 massless bosons to start with, and then there is spontaneous symmetry breaking. One of them still remains massless, photon is still massless, and we have mass of the W, non-zero, mass of the Z. And we wrote down these numbers the other day, 91.177 GeV over C squared. MW was what? 80 point. Check it out, please. Google and give it to us. Google may get your best teacher award at this rate. Yeah. 80.3. Okay. So then we need to write down the vertices of the electroweak part of the theory. So what will happen? An electron comes in and then turns into a neutrino like this. W minus. Anything else? What about a quark? Quark U will come and emit a W plus and produce a. What's the charge of these guys? For instance, but then later we will see that there's one more insertion which has to come in over here, and that is called the cosine of W angle theta C from over here. Now you may say that today we know that there are masses, we also know that there is mixing. So what about here? In principle there is, but then in any process you never observe the neutrino. Therefore, it will be an inclusive cross section summed over all possible neutrino flavors. So there will be an insertion of the corresponding mixing element over here, and all the others will be there. You square it in any amplitude, you get back one. That is why you're still allowed to keep this, whereas here you have to explicitly introduce cosine theta c. Now, when we talk about the standard model has to do with every one of these things. Okay, so you may say that there's a lot of general knowledge, this guy sitting at the blackboard and talking about this, talking about that. Well, that's what it is. And somebody says, what is standard model? Just every one of these things, it has to do with the interactions, it has to do with the flavors, it has to do with the parameters, it has to do with every single vertex. Now, all of you sit in seminars where you say, standard model has been established. What does it mean when someone says standard model has been established? It means that every single vertex is checked. We know the couplings at every single vertex. We know the values of these. These are all, measured at high precision. And the theory makes certain predictions, and the experiment agrees with it. That is what is meant by saying that the standard model is what it is. Okay. You may not like Vigo. Actually, he's a nice guy. There's nothing to dislike about his angle, but you have to know that every one of these is the constituent of the standard model. Every one of these, whether it is a function or running or the names of these constants, etc. So this thing is what is called the charged current. Charged current. So if it is not charged, then what is it? If the current is not charged, then electromagnetism is also an example of neutral current, but this is the weak neutral current. And what are the particles that participate in the weak neutral current? All the standard model particles do. Okay? So there, electron, so it can be an electron, neutrino going to a neutrino, electron going to an electron, U quark going to U quark, D going to a D, S going to S, C going to C. Would you like any other factors over here? No, there's no other factor. Okay. The neutral currents are charged, are flavor diagonal. They are flavor diagonal. Nothing changes at the fundamental vertex of the neutral current. So this here neutral current, so these are all flavor diagonal. Why? Because experimentally found to be diagonal, and in standard model by construction, the Lagrangian is written in such a way that it is flavor diagonal. So if any violation is found of this flavor diagonality, that means it's an interaction that is beyond the standard model. Now you guys at 11:30 will see the next class, which is beyond the standard model. So if you're beyond the standard model, if you find that an electron turns into a muon because of a neutral current, it is not accounted for by the standard model at tree level. At higher order diagrams, you can get that those will be very small, numerically, So any interaction that you say is beyond the standard model, what does it mean? It means that it is not described by these basic vertices. Okay, right? Get it? Get it? So if I wake you up 40 years from now, I won't be here, but you'll know what it means, right? So please keep this in mind. So in BSM, so a lot of BSM talks will talk about flavor changing neutral currents. Okay? FCNC. So if you see FCNC at any appreciable level, that means it is beyond the standard model. This is what you find in uh, Griffiths, but later you will also have to find vertices that involve the Higgs, vertices involving the Higgs. Now, what is the Higgs mechanism good for? You people, by now you know what the Higgs mechanism is good for. It's good to give masters to these W's. Okay? There's something else that the Higgs does. Now, this weak interaction is it distinguishes between left and right. So weak distinguishes distinguishes between left and right.
One question. So when neutron decay happens,
Yes.
then we know that one D plot becomes U plot,
Yes.
and when we draw it, the other plot works. We just draw them as extensions. I mean, doing nothing. So how do we know that it's not having any neutral color there?
So that's by construction in the standard. So if you introduce an additional interaction with light that you are mentioning, then it should have some experimental signature, right? But what you're asking is a very important question, and I'm going to give you a topic to read. Where Z naught is present, but the Z naught is very is very okay. So you're saying Z naught is not going to lead to any decay. Okay. So whenever we are looking at, let's say, radioactive decay of some heavy nucleus, etc., it's because of the charge current. Okay. Leaving aside alpha decay, which is for very heavy nuclei, but if you have lighter nuclei, let us say, whatever, radiocarbon or radio iodine, they all decay through the weak interaction, right? Because again, energetically, that is what is needed. So you're asking, what about a Z naught being exchanged between two quarks sitting deep inside the nucleus? Of course, it's there. The question that you're asking is absolutely right. But the rates of such processes are very small. However, it leads to a very interesting and very important parity violating effect, which was only detected about 15 years ago. It was predicted by Zeldovich. Zeldovich. Do you know the name? You're all cosmic ray people. You must know Zeldovich. So Zeldovich predicted the existence of something called the anapole moment, which is parity violating. So even though you're not crediting this course, you get a project study on anapole moment and you educate the rest of us. This is what happens if you're asking the million questions. Get tracked. You will not find this in textbooks because nobody thought that it could actually be seen and detected. But recently, as in 15, 20 years ago, there are dedicated experiments to okay, so much for chapter 2 of Griffiths, I think. Any questions about all this?
While mentioning density, you said along with ghosts you could add scalars into particles.
Yes.
Won't that scalar just be the Higgs?
No, the Higgs doesn't carry color.
So you can get another symmetry for a scalar, which is not just you.
See, there's nothing phenomenologically or theoretically or logically to say that you can't have elementary scalars carrying color. Just that it's not observed in nature. Okay? So, standard model, we say U is a spin half particle, V is a spin half particle, because we are guided by experiment. But at the level of logic or representations of Lorentz group, there's nothing to prevent these. These are all the great unsolved problems of particle physics. Why is all matter fermionic, spin half? Why is it that all force carriers are spin one? That we know. Gauge principle, there's no other. Why is it that there's only elementary Higgs which breaks electroweak? Why can't it be a fermion? So,
I don't know.
you don't know? This you should know.
Those theorem requires scalar. It does not ask for fermions.
No, those are all circular arguments. Okay, it's only a scalar if it gets the vacuum expectation value. It does not break Lorentz invariance. If you have a field that transforms in non-trivial representation Lorentz group, and you give it a vacuum expectation value, it is spontaneously broken Lorentz invariance, which again is not observed. Of course, at some microscopic level of 10 to the minus 45, maybe Lorentz invariance is broken. Okay. So it's again guided by, so you can only have a scalar, Lorentz scalar to get a vacuum expectation value in order to agree with nature. Okay. Now, how do you test Lorentz invariances? Because forcing me into this corner, let me ask you, what is the consequence of Lorentz invariance that you would like to test in the laboratory? Since I know you people love that experiments. Let's think of some consequences. Yeah. You said CPT. Oh, you didn't say he's not guilty. Okay. He's right. So, as far as we know, the mass of the electron is the mass of the positron. Right? It's a consequence of CPT. And this has been tested at very high accuracy. If I'm not mistaken, it's some 10 to the power of minus 28, 29. How do you know the photon is massive? How do you know that it travels only at a velocity c? All that is theory. You're an experimentalist, okay, at least for the next 2 minutes.
Radiation pressure and those kind of things. That stars and then
So, in light, the best way is to actually measure its velocity. So, when these guys went to the moon, they left some reflectors there and came back strong. Okay, so you can have a laser delay experiment. Okay, you can have a reflection measure. So, those give the best constraints on the velocity of light. Not so much velocity of light, but on mass of the photon. It's bounded experimentally by some incredible number, 10 to the minus 40.
let's say you have a scalar which has a scalar. So scalar is on can only have a U1 spectrum as far as I can understand.
Well, this is an internal symmetry, right?
Scalar is just one dimensional.
Okay, not more than you can have more flavor than one. So here, even when you say U quark and D quark, never mind that they are spin half quark. You have two species of quarks. You have two species of Higgs. Anyway, as it happens in the standard model, you need a doublet. How come this guy knows everything? You've done these courses already? Hmm? You're just a genius. So, in order to set the stage for some more of our discussions, we need to do things like kinematics. If we want to do particle physics, all these wonderful diagrams that we drawn. In addition, we need to look at dynamics, and that will, of course, require us to do gauge mathematics. So, what are the kinds of processes that we are going to look at? For instance, a ion, as we know, decays at rest, right? And it has a lifetime which we have now erased. So its pi goes to mu plus mu, and we know that the magnitude of the momentum of this ion m pi mu squared divided by 2 m pi e, which is obviously also the magnitude of the momentum of the neutrino and the energy of the muon mu squared pi. Here it's going to be c, here it's c squared. And the velocity is e minus c squared. So in order to compute a rate, you actually need to know the velocity and all these things. So this is simple two-body kinematics, but needed to compute like that. What do physical quantities like this? They require a couple of ingredients. What are the ingredients that are needed? One is, of course, the matrix element from an initial state to a final state squared times what we call phase space factor. Space factor. Now, this is true for decays as well as what's the other kind of process that we have? Decays as well as scattering. And in decays, we compute the width or reciprocal of the width, which is the lifetime. And in scattering, what do we compute? Scattering cross section, which could be either a differential cross section or it could be total cross section. But later we will see that there's also inelastic scattering, inelastic scattering, where you may have a doubly differential cross section with respect to this, and also energy of one of the detected particles in case the scattering is inelastic. So these are all the things that are needed to establish structure of a proton and what is called deeply inelastic. So scattering, of course, very simple kinematics is P1, P2, going to P3, P4. So let's say here that this is the S channel, so called, and then you have P1 plus P2 squared, which by definition is called S, and then you have P1 minus P3 squared is T, P1 minus P4 squared. You like to give a name? Latin alphabet. PQRS. And energy momentum conservation tells you that S plus T plus U must be the sum of the. So let us think of a simple case where M1 equals M2 equals M3 equals M4 equals M. So there, in the center of mass frame, in contrast to what other kind of frame can you have? You can have a laboratory frame, you can have the bright frame, you can have the brick wall frame. There are all kinds of frames, but we always like to stay in the center of mass frame. And here, root S is called the center of mass energy. And cosine theta, where theta is the angle between P1 and P3, theta is easy to remember, P minus U by S minus. So these are the basic things that one needs to deal with when it comes to the particle physics and standard model. In the standard model, you have specific predictions for, let's say, the decay rate of the pion, or for the cross section, or P plus D minus, U plus D minus. So, when people say standard model, this is what they mean. They mean that the predicted total cross section is something, and the measured experimental cross section is something else, and you compare the two. And when you say standard model is valid, it means that theory agrees with experiment. Now we have all agreed that the weak interactions violate parity. Okay? What's the simplest way of knowing that it violates parity? So this is a nu and an electron. Violates parity because you're going to introduce a factor over here that is equal to gamma mu, because this is of course a vector particle like this, mu times something. 1 minus gamma phi. Now this assumes that the parity violation is maximal, okay, which happens to be the case as far as we know experimentally. In the charge current, it is maximally violated, but in general, it's not, because if it's a Z, then it's not, and then it's something called GE minus GA gamma. Vector and axial vector. Vector, axial vector. Here, 1 minus gamma phi means that GV equals GA is equal to 1. Okay? Whereas for the Z, it's not maximally violated, so you have to allow GV and GA. Now, this is for parity violation. Parity. But there's one more thing that the weak interaction does, and it violates one more thing. It's experimentally determined already long ago, more than 60 years ago. And what is that? CP violation. In what system? That is parity violation. Cobalt 60 was up here. Chaos. Okay, not decays, but chaos makes it, yeah, decay also. So, chaos. What kind of chaos? Neutral chaos. In contrast to charge chaos. In neutral chaos, they will discount. That's because if you have standard model vertices, standard model vertex is what? Standard model U can turn into an S with the emission of the W. Now, what is the factor that you have over here between U and S? It's the sine of Kabigo's angle. Okay? The angle between the U and the B is the cosine of Kabigo's angle. This is the sine and this. Now, this theory was not complete, and that's why the famous author combination of Glasgow video for this in Miami, then they introduced the charm form. Because this thing looks totally off the line incomplete. So, with these vertices, let's write a couple of second order diagrams. Second order and what? Actually, it's more than second order. It is 1, 2, 3, 4. Fourth order diagrams in the company. Should we do that? You're the genius here to come into. No? You're accused, you decline. So I actually should start knowing the names of some of you. Quickly. You are Aniruddha. Okay, this guy I don't want to know. And this guy also. Okay. You're the guy who set up a WhatsApp group. Your name is the same as mine, so you're not the same. I know that. Yes. I don't want to know him. Aman. Okay. Good. So you have to give me a memory test. How can I remember you? I can remember a handful moment, but I can't remember. Unless you start wearing stickers by my name. So let's do a diagram over here and see what happens. Let's start with a deep quark like this. And let us emit a W, produce a U quark. And this over here, I'm going to start with a K naught with a D, and then this is an S, but going in the other direction, okay? S is going in the other direction. So Aditya taught me that if it is going the other way, then it's an antiparticle, and that is why this is a K naught. defined as an S square going in that direction. Okay. Now, as far as I know, this is correct. W. Okay. And so we have clocks going backwards in this line, like this here. So this is U going in this way and turning into an S dot over here. And then this thing here is a W minus, we don't care about that U. And then this is a D. So this is curious. We started with a DS bar and we ended up with an SD bar. Okay, nothing wrong with that. This is allowed by the vertices of the standard model. So this is an example of K0 going into a K0 bar. So K0 bar can oscillate into one another. But this is not the only diagram, but we can also draw another diagram like this, where we flip this like this. This where the W's are over here. Okay, so this is an S, and a U, and a D. Okay, so this is again K0. K0. So how are K0 and K0 bar related to one another? They are charge conjugates to each other. So C acting on K0 will give you a K0 bar, and C acting on K0 bar will give you a K0. Okay. Very good. What about P acting on K0? Parity is what kind of particles are K0s? We keep saying that they are members of the pseudo-scalar octet. So what does it mean to say something is pseudo-scalar? Minus, like this. Okay. So P acting on K0 bar is minus. Somebody remind me what's the mass of the kaon? Mass of the kaon, roughly. You people should remember all this. How many of you like cricket? Cricket? Anybody? Nobody likes cricket. I love this class. I also hate cricket. But all the guys who love cricket, they know how many centuries the sport. Total waste of time. Much better to remember the masses of kaons. Mass of the kaon. How you tell me? Roughly 495 MeV. Mass of the pion. So how many pions in principle can a kaon be made? Definitely. Any more? 3. 2 or 3. Good. So instead of this K0 and K0 bar, which are not so nice because this is not an eigenvalue equation, you see. Just taking one to the other and taking the other to the one. It's not an eigenvalue equation. So why don't we invent some linear combinations of K0 and K0 bar? This one. K0 bar is the antiparticle of K0. That's the meaning of charge conjugation. C acting on this, C acting on K0. These are pseudo-scalars, so parity acting on K0. Suppose it's an eigenvalue equation with a minus sign. That's it. Nothing more complicated than that. So CP acting on K0 is minus K0 bar. Now I'm acting on both with this. K0 bar is minus K0. So let me define instead two linear combinations K1, 1 by root 2, or K0 minus K0 bar, and K2 as 1 by root 2, K0 plus K0 bar. Just two linear combinations of these two guys. And you will see immediately that Cp acting on K1 is equal to K1. So now it's an eigenvalue equation, and Cp acting on K2 is minus K2. Okay, minus K2. So this thing here, this K1, if Cp is conserved, will decay into 2 pions, and the CP is violated, and this state will decay into 2 pions, and this will decay into 3 pions. Okay? Because they are pseudoscalars, each one of the pions. So the CP properties of the pion gets multiplied. Okay? -1 times -1 times -1. So we expected this will decay into 2 pies. I may have got these flipped, but you should check. This will decay into 3. If CP is conserved, if CP is conserved, but it is found that at some small level, this is actually not true, but one of them actually decays into the other, okay, which also I leave as a small homework problem for you to figure out exactly how CP is violated because of this K0. Okay, so you can figure out.
So the mass of these two states are not the same.
No, they are not.
That's the one decays into.
Yeah. So because they are unstable particles, there's a width. So there's a whole theory of kaon decays and oscillations which you can read.
So, but why is the determinations are also the same?
No, those widths and all they play a role. Okay. So it's complicated. So it's an advanced topic. Okay. So if I had to discuss CP violation, it will take me an hour to write down the entire ideal states of these things with the widths and so on. It's because they are unstable that there is a width also, not just the mass. So you have to look into all those things and then figure out exactly what are the parameters that enter. You can have a look, part of the data book, just Google it, look at the section, review section on kaon decays, and you can have a look. So CP violation leads to what you call a forbidden decay. Up until the beginning of the century, the only evidence of CP violation was in the K0 K0 bar system. But in this century, we have built what are called B factories, where there are B mesons produced in large numbers, and the B being a very heavy particle has a large number of final states. And from that, we have explored CP violation in a very detailed manner. Here, this is a very pure system. It really can't go anywhere else, right? Because you have to conserve electron number, you have to do all kinds of things, so that you have only a handful of decays with you. Not many particles available that are lighter in electrons, except for the pions. You can also have, say, emission of a photon, some rare decay where you have emissions of photons, or you can have these things decay into neutrinos at very, very small branching fractions. Many of these things are. So what does it say about pions? Does it say anything? You can have a look. And then I can also have a look. It's just a little bit on Tuesday. But on Tuesday, somebody is supposed to give a demonstration of NCAT, some of the notebooks. Okay. The notebooks that I have are pretty old and they don't even run on present versions of it. So you guys, you should all try to install these things and get it going so that you get an on-hand experience. Okay, so I think I'll stop here and see if there are any questions. Okay, and then we will move along with this book. Also.
Mesons, are they also pseudoscalars?
Which one?
Mesons.
Uh,
Always seen as pseudoscalars.
Good question. Even the kaons, it's not so. You can get the K star, for instance, which is a radial excitation of. So you can have vector mesons also with the same quark content, but with angular momentum among the quarks. So the B system, it shows a lot of diversity. It has all kinds of final states, all kinds of excited states, and you can decay into a large number of final states. The mass of the B is about 4.5 GeV. So you can imagine how heavy it is. It is, M is just 139 MeV. So you're looking at 3 orders of magnitude. Not quite. Let's see. Proton is about a GeV. This is about 5 times the mass of a proton. The B is. So it can gain all kinds of states. And it can show very interesting mixing behavior, large numbers of this kind of mixing between B. So you have a BB bar oscillation, you have a BS bar oscillation. You also have oscillations among charm mesons. The charm mesons are called the D mesons. Okay? One charm and one light quark. They're called D mesons. So they also show mixing. But the charm system does not show any appreciable CP violation. It's only the B and the K which do. Again, because these peculiarities of dim cancellation. Okay. So I think I'll stop this.